This video is a first principles guide to molecular design for two-photon absorption, or 2PA. We will explore how to engineer the quantum mechanical transition amplitude to create molecules with stronger 2PA properties. Improving 2PA is achieved by manipulating interactions through four fundamental levers. These include maximizing transition dipoles, minimizing energy detuning, maximizing charge redistribution, and forcing constructive interference among pathways. The 2PA amplitude is a coherent sum over actual molecular eigenstates. The key levers for manipulation are transition dipoles and energy detuning, which directly influence the components of the transition amplitude equation. For low-energy 2PA, in a quasi-1D dipolar chromophore, the strength strongly depends on the change in permanent dipole moment upon excitation. This highlights the importance of lever 3, charge redistribution. In higher energy 2PA with resonance enhancement, the denominator of the transition amplitude becomes critical. The optimal condition is near resonant, which relates to lever 2, energy detuning. Care must be taken to avoid issues like sequential absorption. Symmetry reorganizes the eigenstates. Centrosymmetric molecules, such as those with quadrupole and octupole architectures, can place oscillator strength into channels uniquely favorable for 2PA, utilizing lever 4, constructive interference. Push-pull systems operate on a trade-off surface. Maximizing the 2PA amplitude requires a balance of donor-acceptor strength to maximize the product of the transition dipole and charge redistribution terms, balancing lever 1 and lever 3. For strong 2PA, conjugation must remain electronically coherent. It is not just about making the chain longer, but ensuring the electronically active conjugation pathway is both long and coherent, maintaining good orbital alignment. Planarity is essential as it preserves through bond coupling. As the dihedral angle grows, conjugation weakens, and transition dipoles drop, reducing 2PA intensity. Vibronic coupling is a key factor. Molecular vibrations that modulate charge redistribution can lend intensity to a 2PA transition. The best chromophores exploit both electronic charge transfer and favorable vibronic borrowing. Branching requires a coupled core for superadditive growth, leveraging lever 4. If branching simply acts as independent sums, you get molecular bureaucracy instead of cooperative enhancement. The local field amplifies the transition. You are designing the molecule and its environment. Solvents, host matrices, and hydrogen bond networks can dramatically amplify the excitation-induced dipole change. The golden rules of 2PA design involve maximizing the transition dipole moments, increasing the change in permanent dipole, reducing detuning, interfering constructively, and controlling the vibronic structure. Various molecular motifs like push-pull dipoles, quadrupoles, octupoles, metal complexes, and rigidified triphenylamines offer unique advantages for optimizing 2PA properties through their structures. Strong two-photon absorption results from the precise engineering of orbital energies, wave function overlap, and intermediate state detuning. By controlling these factors, we ensure the transition amplitude grows rather than cancels.